All right, folks. So we're going to get started on the second half of class, and we're going to take a look at 10.4, which is integrals with discontinuous integrand. Okay, so one of the key features about 10.3 was that everything that we were looking at was continuous on a given interval. And what's going to be different now is that we're going to be experiencing places where the functions are not continuous at the points that we're looking at, okay? So I'm going to go ahead and share my screen so that we can take a look at the 10.4 notes. Okay. All right, so we've got 10.4, we've got discontinuous integrals. And what we're going to be looking at is things that we know, okay? So let's start there. We know that if we have a function, that's not a horizontal line, if we have a function and we're trying to find the area, that as long as we have bounds, like from A to B, that we can find that area, okay? So in all of Calc 1, when you learned about integrals, there were no sort of like funny business sort of situations, all right? But what we learned in this last section, 10.3, was that sometimes we could look at situations at the ends, right? Like looking at end behavior. So does this function drop quickly enough so that I could find that area? Or sometimes we looked at like the right end behavior. Did this end drop quickly enough so that we could find that behavior or that area? Okay, so that's what we really focused on, was like the end behavior. And so what's going to be different about this section is we're looking now at a lot of the same graphs, okay? So we're going to see a lot of the same pictures again, but what we're going to be looking at is specifically, hey, there's a vertical asymptote here, right? Like let's say there's a vertical asymptote. I want to know if I find the area from, let's say this is x equal a to a stopping point, let's call this B. Can we find this area? Okay, so before it was, in this case, it was, does the function drop quickly enough? All right, that's kind of what we were trying to understand. But in these cases, we're looking at, does the function get close to the vertical asymptote quickly enough? Okay, so we're not looking at whether it gets close to a horizontal asymptote. We're actually looking at, does it get close to the vertical asymptote quickly enough? All right, so that's the biggest difference between 10.3 and 10.4. So again, we're going to have a few different cases about what happens when we're getting close to these, all right? So in this case, we have a situation where we're going to be finding this area, and the top bound is going to be the one that causes the issue, okay? So B is the problematic one because there is an infinite discontinuity at B. So we're actually gonna use the same letter T, but we're gonna take a limit as T approaches the value that we want. And we're gonna see if we can integrate and then plug in our numbers and then take the limit does it still give us a number? Then yes, it converges. And if it gives us infinity or negative infinity, then it's going to diverge. And then we're going to take a look at a case where there's an infinite discontinuity at the bottom bound. And so we're going to take our a and we're going to replace it with a t, and we're going to find that limit as t approaches a from the right. And then we're going to take a look at one last situation where maybe you have a and b are both totally fine, but there's some point in the middle where the function has an infinite discontinuity. And so in this case, the split happens at the discontinuity. Okay, so let's maybe write that down, that our split occurs at our vertical asymptote. Okay, so C is where we have that vertical asymptote. So in 10.3, we could pick whatever number we wanted, but in 10.4, if the whole function contains a discontinuity, we have to split it at the discontinuity, okay? So let's go ahead and take a look more deeply at case number 1. So case number 1 is a situation where we're going from A to B, and there is a discontinuity at B. Another way to say that is there is a vertical asymptote at x equals B. All right, so that's problematic for us because it's not always going to give us an answer. If the function does not get close enough to that vertical asymptote fast enough, then it diverges. But if it does get close to that vertical asymptote fast enough, then we can actually find an area, okay? So you'll notice that there's sort of these like the minus and the plus signs, so like coming from the left or coming from the right. And so let's make sure that we understand why that is on a given diagram, all right? So I'm gonna sketch a general diagram right here. And when we have our function, all right, and we have, let's say, that vertical asymptote right here at x equals b. And we've got some a over here, and we want to see whether or not this area has a numerical value or if it goes to infinity, okay? Now, if I think about taking the limit, like I'm picking a t value, that t value is going to actually be like somewhere here. And then I want to see as it gets really close to b, what happens. So my t is approaching the b from the left-hand side. T approaches b from the left hand side, okay? That's why we have that minus sign there. And when we take a look at case number 2, it's gonna be flipped. That's why we have a plus sign, because we're gonna be approaching from the right-hand side, okay? Okay, so let's take a look at our first example, right? So this function we saw earlier, 1 over the square root of 3 minus x, and we hand drew that diagram, but this one I cut and paste from Desmos. We have a situation where we've got a vertical asymptote at x equals 3, okay? I know that line's not very vertical, sorry. But I want to find out how I can, if I set my starting point at 0 and I say, let me find this whole area, does this function get close to that vertical asymptote fast enough so that I can find an area? And so let's set up our equation. Limit as x approaches 3 from the right? 3 is my vertical asymptote, and my picture is on the, my picture is on the left-hand side, so I'm approaching 3 from the left, all right? And the limit from, the integral from 0 to t of 1 over the square root of 3 minus x dx, all right? Now, again, we just did this integral, so we know that we're going to get the limit as x approaches 3 from the left of -2 square root of 3 minus x, and I'm going to plug in t, and I'm going to plug in 0. Let's go ahead and keep this -2 out in the front. I'm going to get 3 minus 3 when I plug in 3 for t, and then minus square root of 3 minus 0. Okay. Now that 3, this one right here, this is the one that we plugged in. We're really plugging in numbers like 2.999999999 because we're approaching 3, but from the left-hand side. And so as this gets closer and closer to 3, the t value, this goes to 0. And so what we end up with is -2 times negative square root of 3, or we end up with an area, that pink area is 2 root 3. Okay. Any questions on this example? All right. So case number 2. Case number 2, we have a discontinuity at B. So that does not change. We have a vertical asymptote at x equals B. This time, however, we are going to be looking at, did I type that wrong? I did, sorry. Sorry, folks, this is why you always proofread. This should say from A to B, and our vertical asymptote is actually at A, x equals A. Okay, so let's get a diagram going. All right, just like we did before. We've got our function that is going to have a vertical asymptote at x equals A. And then the function that we're looking at is not on the left-hand side of this, but rather on the right-hand side. And then we've got some stopping point. And so we want to see on this side, does the function get close enough to that vertical asymptote fast enough so that we can find the area? Or does it approach that vertical asymptote but too slowly, and then we wouldn't be able to find that area? Okay. Now, if we look at a t value, we're going to be picking a t here, and we're going to be approaching A from the right. So that's why when we have this, we have t approaches A from the right-hand side. All right, so T approaches A from the right-hand side, and so that's why we have the plus sign there. Okay, so let's take a look at our examples here. All right, so very similar to things we've seen before, we've got our 1 over x. It is our rational function, our inverse function with the 2 branches. And this function does have a vertical asymptote at 0. And let's be more specific. This is at x equals 0. And so if I want to find the area between 1 and 0, I'm looking for this area right here. And so our question is going to be, does this function get close to this vertical asymptote fast enough and give us a number or not? All right, so we've got the limit as t approaches 0 from the right. And so we're going to replace the 0 with a t, and we're going to keep the top bound as a 1. And we have 1 over x dx. And this is one of our very, very common integrals that I think you all are super good at now. It's just going to be the natural log of x, and I'm going to plug in 1, and I'm going to plug in t. And so I'm going to have natural log of 1 minus natural log of 0 from the right. Natural log of 1 is 0. And again, if we kind of think to this natural log graph, looks kind of like this. When we approach 0 from the left, from the right, what y value does that function get close to?
Negative infinity.
Negative infinity, good. So I have 0 minus that negative infinity. And again, this is negative infinity because that part of the function goes down towards negative infinity. So we end up with a situation of 0 plus infinity or infinity. So we can say that this improper integral diverges.
So will we see that it doesn't drop fast enough, or that it does drop fast enough?
Diverges means that you get infinity or negative infinity. You don't get a number. That means it does not get close fast enough. Okay, so like this red line here, as it traces up, doesn't get close to that orange line fast enough for us to seal off an area.
Okay, I get it now.
Cool. All right, let's take a look at example number 3, okay? So I'd like you guys to start with your diagram. Go ahead and shade in the region that we're looking for. See if you can set up the integral that you need along with the limit, and see what rules you need to find that integral, okay? All right. So based on the picture, even when I'm shading, and this is why for this section I chose to like get the or like print out the pictures for you. I bet we can all look at this diagram and be like, yeah, this curve gets close to that vertical asymptote way faster than the other one does. And it's going to turn out that we'll be able to find the area of that orange section, okay? But let's kind of see how we get there. So we're setting up our integral. We're going to take the limit as t approaches 0 from the right of the integral from t to 1 of 1 over x to the 1/3 dx. We can rewrite this as x to the power of -1/3, okay? And then all we need to take our integral is the power rule. So x to the -1/3 plus 1 is going to give us 2/3. And then the reciprocal of that is 3/2. I'm going to plug in 1. I'm going to plug in t. So I get 3/2 times 1 to the 2/3 minus 3/2 times 0 to the 2/3, or 0 from the right, so like a really, really, really small number. And so 3/2 of essentially 0 is going to go to 0. And so this part, if it gives me a number, then we're in business. We got an area. And it turns out that gives us a final number of 3/2. And so that 3/2 represents the area that we shaded in the beginning. Okay. So before we take a look at the last two examples, I'm just gonna zoom out for a second so we can see both of these graphs on the same page. And when we look at the graphs, we notice that first graph is kind of like far away from the vertical asymptote. And so it makes sense that it wasn't getting close fast enough, so therefore it diverges. Whereas the example number 3, from the picture alone, we can see that it gets pretty close to that asymptote pretty fast. And so therefore we're able to find an area for it, okay? You can almost think about this as like, so I think about it like I have some friends who, you know, when they get in a relationship, like immediately, like they're dating this person for like 2 days and they're like, oh my goodness, we're so in love. And you're like, oh wow, that moved real fast, right? And so like some of those folks choose to stay together or they converge into a relationship. But then you have other folks who are like, look, if that person catches feelings, I am out of here, right? Or you kind of keep someone at a distance, like you don't let them get close fast enough. You might not be staying with that person for a long time. Maybe that relationship wasn't meant to be, okay? So we've got, is it getting close fast enough? Yes, it converges. Is it getting close fast enough? No, then it diverges. All right, we got one last case here, all right? And so this case is a situation where we have a whole interval from A to B, but somewhere in that interval, there is a vertical asymptote. And so we need to be careful about where that asymptote is, and where it is has to be our splitting point, okay? And then both sides of that vertical asymptote have to get close to the vertical asymptote fast enough in order for us to say this improper integral converges. So let's take a look at example number 4. Not quite sure why I left the picture so big, but it is. Okay. So based off of our reasoning from earlier, we know that x minus 3 means that we have a vertical asymptote at x equals 3 because I shift the function over 3 units to the right. And so that leaves me with an asymptote right here. Okay. And so our question is, I want to find the area from 0 to 3. And then I know there's a gap in the function. Then separately, I want to see what about this area on the other side from 3 to, and I think I went too far, 3 to 4. Okay. So I'm stopping at 4, I'm starting at 0, but in between there's that vertical asymptote, and that's a problem. And so when we split our integral, we need to find the integral from 0 to 3, and then separately, we need to find the integral from 3 to 4. And so that's going to look like this. The integral from 0 to 3 of 1 over x minus 3 squared dx plus the integral from 3 to 4 of 1 over x minus 3 squared dx. So same function, but we're splitting it at the discontinuity. And so this means now that we've essentially ended up with a question like we had before, but we have 2 different parts. We have to do both techniques to make sure that this works. Let me actually move this down here where I have a little bit more space. Okay. So for the first one, we're looking to approach 3 from the left. So we're going to say the limit as not x, as t approaches 3 from the left, from 0 to t of 1 over x minus 3 squared dx, plus the limit as t approaches 3 from the right of t to 4, 1 over x minus 3 squared dx. Now this was an integral that we saw back in 10.3. So I'm not going to go through the work again, but we'll just jump straight to the actual integral, which is going to be negative 1 over x minus 3 to the first power, plug in t, plug in 0. And then we're going to do the same thing over here. And the nice thing about splitting the integral's the same. So once you do it one time, you don't have to do it again. And we're plugging in 4 and t.
Professor, is there supposed to be a squared on there? 1 over x minus 3 squared?
Not after we take the integral, no.
Sorry.
Yeah, because we do the power rule, right? So that power of -2 becomes a power of -1. All right, let's plug in for this first one over here. I get -1 over, I'm approaching 3 from the left, so let's pick like a 2.9 minus 3 plus, because it's minus 1 over 0 minus 3. And so from here, I can immediately tell, like, this one's going to be fine. -1/3 is totally fine. But this right here is going to create a problem because we're going to end up with a negative infinity. Okay? So this diverges. And if one part of it diverges, it doesn't matter what the other part does, because according to our rule, both sides need to be convergent. So as soon as you find that one of the sides diverges, you don't have to worry about checking the other side. You can just say that the whole integral, the improper integral, diverges.
So I have a question on that first part. You plugged in 2.9.
Hold on one second. So in a problem on a quiz or a test, if we see that it's divergent, can we just stop and say it's divergent? I mean, if you show me all of this up until here and you can show me that one part of it diverges, then yes, you can say the whole thing diverges on a test or a quiz. Okay, sorry, what was the other question?
On that first part, you plugged in 2.9.
Yeah.
How come you didn't plug in 3?
You could plug in 3. I was just thinking because we're looking at numbers that come from the left. And so sometimes it's easier for me to remember that I'm not plugging in 3 and I get 1/0. And then sometimes I feel stuck. But if you feel confident knowing 1/0 is getting to infinity and that's why it diverges, then that's fine too.
Oh, okay. All right.
Okay. All right.
And then I had one more question.
Sure, what's up?
If you come across a problem like this, and let's say that instead of from 0 to 4, it was like 2 to 4, could you just use that symmetry rule on this whenever you're evaluating it, where it's like 2 to 3?
Yeah,
Okay.
I see what you're saying. Yep, exactly. And so I intentionally picked like this one and then example number 5 is not symmetric. So we
Yeah.
can use that shortcut. But if it were 2 to 5, 2 to 4, or even like 0 to 6, then that would be fine.
Okay.
Okay. All right, folks. We got one last example here. And let's take a look at this one. So we've got the integral from -2 to 7 of 1/x+1 to the 2/3 power. Now, this tells me that there is a vertical asymptote at x equals -1. And I can see from the graph that I've got a situation here where at x equals -1, there's a discontinuity in my function. Now, based on this picture, what do we think? Converge or diverge?
Converge.
Converge, yeah, exactly. So we're thinking this is going to be converging, and now we just need to figure out what value it converges to. Okay, so that's why I kind of think the graphs here are helpful, because they help us figure out in advance, like, all right, are we going to get a situation that converges? Does it look like it? And in which case, it's almost like a good check for our answer at the end. Okay. So the splitting point for this integral then is going to be at -1. All right, so I'm going to go ahead and write my two integrals. I've got the integral from -2 to -1 of 1 to the 2/3. And then plus the integral from -1 to 7 of the same function. All right. So this is going to be the limit as t approaches -1 from the left. And I'm just going to write this as x+1 to the -2/3. Set myself up for that power rule right there. -1 from the right of t to 7, and same thing, x+1 to the -2/3. Yeah. All right. So let's take our integrals. We're going to need to use our power rule here. And u sub, but this coefficient is 1, so we don't really need to worry about it. So I get x+1 to the power of -2/3 plus 1 is 1/3. And the reciprocal of that is just 3. And I'm going to plug in t and -2. And I'll do the same thing over here, except I'm approaching t from the other side. And whoops, I'll get 3x plus 1 to the 1/3 and plug in 7 and t. Okay. Now let's plug in all of our bounds. So at first, I'm going to plug in -1. All right, so I'm going to get 3 times -1 from the left. And so this is going to go to a 0 to the 1/3. Minus what happens when we plug in -2, this becomes -1 to the 1/3. So all of this first part in the bracket is from the first limit. And then when we do the second one, we'll get 3 times 8 to the 1/3 minus 3 times 0 to the 1/3. And when we simplify, we'll get 0 plus 3 plus, let's see, the cube root of 8 is 2, so 3 times 2 gives me 6, and then minus 0, or 3 plus 6, or 9. And so we have confirmed our initial guess based on our diagram that those functions looked like they were getting real close to that asymptote real fast, and we were able to find that the area, which I didn't shade, but I'll go back and shade right now, from -2 all the way to 7, so this part down here. All right, so the two areas on the either side of that vertical asymptote, they approach that asymptote fast enough that we're able to find the area. And that area of the green region is 9.
And do you want us to write that it converges?
Yeah. All right. So folks, that is chapter 10. All right, we did the first part on Thursday where we talked about L'Hôpital's along with other strategies on how to handle those situations where we have 0 over 0 or infinity over infinity, different types. And then today we were focused more on like the actual area, like how do we find area using limits when we have either horizontal asymptotes like in 10.3 or we have vertical asymptotes like in 10.4. All right. So that's it for today's lesson. If you were all set, you're welcome to take off. If you signed up for an exam 1 debrief today, make sure to check your calendars. You remember what time. You guys have been super great about showing up. And I will also check my calendar to make sure I'm there for any slots that have been signed up for. Okay.